So let's get started with this free response question. Because this is question number 1, that tells us that we are working with our calculators for this, and it also says that at the top. So the first part says, let R be the shaded region in the first quadrant enclosed by these graphs, as we can see. So I'm just going to kind of highlight these in their respective colors just so that we can see what we're dealing with. I like to color code my problems. And it's enclosed by the y-axis. So it wants us to find the area of the region R. Now, something that's really tricky about this question is that it almost looks like this intersection is happening at 1, but we can't really be sure, and I think maybe it's slightly before that. So we want to actually grab our calculators and find where that intersection point is. So the first thing we're going to do is graph our two equations. So I'm going to type those into my y equals. Now we're going to change our window so that it matches the graph that is shown on our paper. Next up, once I see the graph, I'm going to hit second trace intersect and then follow the directions to find where they meet up. So now I'm going to go back to my home page and store this value. So I check that X is the intersection point, and then I hit store alpha A, enter, and that stores this intersection point as A. So we found our intersection point and stored it. So the next thing that we want to do is move on to part A. So it says, let's find the area of the region. So remember, when we're doing area, we only need to do the integral without thinking about volume of revolution or anything like that. So the area is just going to be the area under the curve from 0 to that intersection point. So we're going to use A in our calculators of the top minus the bottom. So that's going to be the red curve, e to the negative x squared, minus our blue curve, 1 minus cosine x. And we want to be super duper careful that we put this in parentheses, because if this second piece is not in parentheses, when we subtract it, we're not going to distribute that negative if we don't put it in parentheses. So be really, really careful that that's how you write this. And then since we get our calculators, let's go through this in the calculator to find that value. So to do this integral, we're going to go to Math 9, and then because we stored this in y1 and y2, I'm just going to pull those up. And then to be extra precise, we're going to use A for our upper boundary since we stored that. All right, we got 0.591, so let's move on to part B. So part B is now asking for the volume of the solid generated when R is revolved around the x-axis. So the x-axis means that when we set up our integral here, we're going to do this with respect to x, so dx. And then our volume formula, remember, is going to be pi times our radius, but in this problem, let me zoom out a little bit. In this problem, we are going to rotate this around the x-axis, and so we're going to have to use the washer method because there's this gap right here, and so it's not fully connected to the x-axis. So we'll have to use the washer method. So we're going to need to do our big radius squared minus small radius squared. So my big radius is going to connect the upper curve to the axis of revolution, and then our small radius is the part that we're taking away. So that's going to connect this lower curve to the axis. So our big radius comes first. That's going to be e to the negative x squared, and we want to square this because remember we're doing our volume here, minus the little r squared is going to be 1 minus cosine x. The last thing we need before we can put this in our calculator is the boundaries. So again, our x values are going from 0 to that intersection point A that we found earlier. So now we can throw this in our calculator and find the value. So we're going to type this integral in using y1 squared minus y2 squared, and that's going to help us make fewer typing errors as we put this in our calculators. And we got 1.747, so we can move on to part C. All right, so part C is talking about cross sections. We've got square-shaped cross sections, and we want to find the volume using those squares. So I do need to figure out the area of just one square, so let's go take a look at our problem again. So we had each piece was a square perpendicular to the x-axis. So this will be one side, that distance from the top curve to the bottom curve. So the area of one square is going to be the top curve minus the bottom curve. And so again, I want to use parentheses when I'm putting that in my function, but we can just simplify this to be minus 1 plus cosine of x when we distribute that negative there. So this is going to be the area of 1 square, and so we're going to have to put this into an integral to actually calculate the overall volume. So to calculate the volume of this solid using the cross sections that they described, we're going to take that area of 1 square with respect to x, because again this was perpendicular to the x-axis, and we need our boundaries, which should stay the same as they've been in the previous problems because we're not switching this to y values. Those are going to stay x values, and now we can throw this in our calculator. So this problem we're going to do the integral with extra parentheses because we want to do y1 minus y2 all squared and then put our boundaries. So we get 0.461. Let's move on to that next problem. All right, so take a second to read this to yourself and then we'll get started. So part A is just asking for the area of R. So that means we can just do a regular old integral of top curve minus bottom curve. And so the top, they told us, was y equals 6, that horizontal line y equals 6, minus the bottom is our 2 square root of x curve, and this is with respect to x. Our boundaries are going to be the x values from 0 to 9, and this is not a calculator problem, so we actually have to do this by hand. The reason I know it's not a calculator is because A, I'm telling you, and B, it said at the top of the page it's question number 4. So to do this problem by hand, I would probably rewrite this so that we have 6 minus 2x to the 1/2 rather than that square root. I think it's just easier to look at. And now we can do the integration. So the integral of 6 is 6x. The integral of 2x to the 1/2, we're going to get x to the 3/2 because we add 1 to the exponent, and then divide by the new exponent or multiply by its reciprocal 2/3. And because we already had that 2 in front right here, we're going to multiply that by 2/3 to get 4/3. Keep my boundaries, 9 and 0. So now to continue, we're going to plug in 9, so I'll have 6 times 9 minus 4/3 times 9 to the 3/2, all minus 0 plugged into everything is just going to be 0, so that one's kind of nice and easy for us. And so now we can simplify this. So 6 times 9 will give us 54 minus 4/3 times. So we want to do the exponent first. So 9 to the 3/2 really means the square root of 9 cubed. So the square root of 9 is 3. Cube that and we get 27. So now we've got 54 minus 4/3 of 27. So 27 divided by 3 is 9 times 4 is 36. And 54 minus 36 is 18. So that is problem A. So now problem B is asking us to write but not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. So let's take a look at our picture. So we are going to take this shape and rotate it about y equals 7, which is above the graph. So we're going to have to use our washer method because when we spin this around, there's going to be this empty sort of area between our shaded piece and that axis of revolution. So we're going to need to have a big R and a little r. So our big R is going to be the radius, the distance between the axis of revolution and the farthest curve. So that's going to be big R. And then little r is what we're taking away, so the empty space. So our big R is going to be top minus bottom. So 7 minus the curve to square root of x. And little r is going to be top minus bottom, so 7 minus 6. So our volume is going to be pi times the integral of big R squared minus little r squared dx. And we know this is dx because we're rotating it about a horizontal line, just like the x-axis. And so then our big R is going to be 7 minus 2 root x, and our little r is going to be 7 minus 6, or we could just put a 1 there. And now we need our boundaries. So the boundaries are going to be x values. That's from 0 to 9 in this case. So part C is now talking about cross sections. So we're going to do the cross sections. It even gives us the range here, the y values. because we are going perpendicular to the y-axis. It's also a rectangle whose height is 3 times the length in base region R. So what does that mean? We first have to think about the area of each individual rectangle. So the area of a rectangle is base times height. So if we go up and look at our shape here, we need this to be perpendicular to the y-axis. So that means it's going this direction. So if this is the base of each rectangle, that means that it's going to be our curve y equals 2 square root of x minus the y-axis, but this would have to be in terms of y. So we're going to have to solve this equation for x. So we can start by dividing by 2, so we'll have y over 2 equals the square root of x, and then squaring both sides, and we'll get y squared over 4 equals x. So this is now the curve that we have sketched right here, but in terms of y, so that we can actually subtract that minus our y-axis. So going back to part C, we said one base was y squared over 4, and then the height is 3 times that. That's what it says in our problem. So 3 times y squared over 4. And now just to simplify this a little bit, we'll have 3 over 16 y to the 4th. So that's the area of one of these rectangles. So to actually answer the question, we need to write the volume, which is going to be to add up all of the areas of these rectangles. So we're going to do the integral, and this is with respect to y because we're perpendicular to the y-axis here. And so our boundaries need to be the y value, so from 0 to 6. And then that would be our final answer because this is non-calculator, so that's all we can do here.